Hello, class. I want to cover 3.4, the chain rule. And it's very important that you learn this. All of the sections are important, but so much of our differentiation depends on using the chain rule. So it's really important that you learn this. You might not pick it up just immediately, but if you keep working at it, you'll get it. So we're talking about how do we find the derivative of a function like this? And what this is a composite function. So this is a composite function. And that's when we have to use the chain rule, is when we have a composite function. Now, if you remember back from college algebra, let's talk a little bit about how it's a composite function. If we let little f of x equal cosine x, that's going to be our outside function. How do I know that? Well, in this case, it's actually, it's on the outside. Here's our function in case you can't see it real well. It's cosine of x squared. So in this example, it's actually on the outside. And let's let little g of x equal x squared, and that's going to be the inside function. And it's important to identify these. You know, when you get used to doing it, or maybe even before, maybe immediately, you'll be able to recognize these. But you need to recognize which is the outside function and which is the inside function. Now, if you remember from college algebra, the way a composite function goes, you can either write it with that notation, which I actually like this because it shows the inside the outside. There's another notation, you might remember the fog, and that is not multiplication. That means it's a composite. But if you look at it like this, so my outside function is cosine. So I go cosine, and then I'm going to put the inside function inside. Now, all of that is just algebra. We haven't done any calculus yet. So now when I go, and this is f of x, it's cosine of x squared. Okay, now we're ready to do the calculus. So before we do that, we've got to get the chain rule. But this is what we want to differentiate. So the way the chain rule goes, if g is differentiable at x, so remember we're talking about something like this, f of g of x. So if g is differentiable at x and f is differentiable at g of x, then the composite function f equal, and they're using the fog notation, defined by big F of x equal, now they're using the other notation, is differentiable at x, and f prime is given by the product. So the chain rule, it does, it's not the product rule, but it does use a product. So the derivative of this composite function is the derivative of the outside with the inside intact times the derivative of the inside. And the reason they call it the chain rule is it goes in a chain. If you have a composite of more than two functions, and we'll see that, the derivatives go in a chain, or this pattern goes in a chain. So the Leibniz notation is if y is f of u and u is g of x are both differential functions, then dy dx equals dy du times du dx. And we don't really use that notation that much in this class. I tend to use this notation more. So let's go back to our function that we had. Our function looked like this. And we identified it, the inside and the outside. So the derivative of this is going to be the derivative of the outside. Derivative of cosine is minus sine. We leave the inside inside, and then we multiply times the derivative of the outside. Of the inside, derivative of the inside. So we have f prime x equals a minus 2x. Usually we write it in this order, like with our coefficients first, and then the simplest term next, which is x, and then this. So this is a chain rule. Now, one mistake I see a lot of times people make, they do the derivative of this, and then they do the derivative of this inside while it's inside. That's not correct. You need to do the derivative of the outside with the inside still the way it was, times the derivative of the inside. Okay. So let's look at our next example, which I'll look at that for just a second while I get this ready. And take a little sip of my Mountain Dew. Okay, now we're ready. And this is just another page that is explaining about it, and then we'll do an example. So, in using the chain rule, we work from the outside to the inside. Formula 2 says we differentiate the outer function at the inner function. So in other words, we still have it evaluated at the inner function. The inner function is still inside the outer function. And then we multiply the derivative times the derivative of the inner function. So we do the derivative of the outside with the inside still inside. So here's f prime, inside still inside, times the derivative of the inside. Okay, here's an example. So we want to find f prime x. And here's what we have for f of x. Now, in this example, we can kind of see that there's an outside and an inside. That's not always going to be the case, but sometimes it's really easy to just see this is outside of this function. So our inner function little g of x equals the x squared plus 2x. And the outer function is equal to the square root of x. And you can see that if you do the composite, and let's call this, let me call that little f of x. Okay, so the composite would be equal to the outer with the inside. Okay, and one thing to remember is that this little, the square root of x is also x to the 1/2. Because remember, we change it to that form when we're differentiating. Okay, so now we're ready. Okay. So I'm going to rewrite f of x as x squared plus 2x to the 1/2 power, because that's what the square root is. Then f prime x, so we're going to do the derivative of the outside. So we bring down the 1/2, we're using the power rule, and we subtract 1 from 1/2, giving me a minus 1/2. And then we multiply times the derivative of the inside. So the inside derivative is 2x plus 2. And that's our answer. We can rewrite it if we want to. We can rewrite it as 2 times x plus 1. We factor out the 2 from here, and that's going to be in the numerator. And then in the denominator, we've got a 2 times the square root of x squared plus 2x. And we can cancel the 2's if we want. So then it's just x plus 1 and this is f prime x plus 1 over the square root of x squared plus 2x. Okay, so that's how we do that. Now then, let's look at another example here. Okay, let me just do this on the back. Okay, so let's call this B. So find f prime x, big F prime x, and f of x is equal to cosine x squared. Now, this is different. This is different from cosine of x squared, which is the first problem we did. In this case, the squaring is the outside function and cosine is the inside function. In this example, it's the other way around. Cosine is the outside and x squared is the inside. So you can see, and there's different answers. So you can see that it does matter which is the inside and which is the outside. So my outer function is f of x equal x squared, little f of x. And my inside function or inner function, however you want to say it, my little g of x is equal to cosine x. And you can see, you can check that if you've got it right, just put it back together again, do a composite of these two functions of the f with the g inside. So the f is the squaring function and you're putting g inside. So that's cosine x squared. Okay, so now we're ready to take the derivative. Okay, so f prime x, we're going to take the derivative of the outside. So the outside is the x squared. So we use the power rule and we bring the 2 down. Remember, we leave the cosine x inside the outer function in this first part of the product. We subtract 1 from the exponent, and then we multiply times the derivative of the cosine function, which is minus sine x. And then we can just rewrite it and that's different from the derivative that we got when we did the other one. They're not the same. Okay, let's see what else we've got here. So sometimes what makes it kind of hard is when we have to combine some of the different rules. Like this is the power rule. This one's not really very difficult. The power rule combined with the chain rule. And we do this a lot. So if that's all you're doing, it's not too difficult. So you can either write it in this notation, bring down the n, and you subtract 1 from n, but then you've got to do times the derivative of the inside, which is the u. Or in this notation, we bring down the n, leave the g of x inside, n minus 1 times g prime x. So here's an example. H of t equals t to the 4th minus 3 raised to the 5th. So our outside is f of t, because our variable's t here, equal t to the 5th. And my inside is g of t equals t to the 4th minus 3. And then you can check, but that will work. So when we go to do h prime t, we're going to bring down the 5. And then we leave the inside inside. And we subtract 1 from the inside. And then we've got to go times the derivative of the inside. So we've got to, if I write out what I've got to do, I've got to multiply times the derivative of this. So I've got 5 times 2 to the 4th minus 3 to the 4th. And then when I do the derivative of this function, it's going to be 4t cubed. That's the derivative of this, bring down the 4, subtract 1 from the exponent, and the derivative of minus 3 is 0. So you can rewrite it. It's going to be equal to 20t cubed times t to the 4th minus 3 to the 4th power. So I just multiplied this and wrote it in a different order. So that's h prime t. Now let's look at another one. Let's call this one A. Let's call this one B. And we've got big F of x equals x squared plus 2x plus 3 to the 7th power. And I bet you can figure out what the outside is. It's x to the 7th. And the inside is the x squared plus 2x plus 3. Okay, so I figured that out by now. So when we go to do the derivative, we're going to bring down the 7 using the power rule. Subtract 1 from the exponent, don't forget that. And then we're going to multiply times the derivative of the inside. So that'll be 2x plus 2. Okay, and that's my answer. I could rewrite it. I'm not gonna, but I could factor out a 2 and multiply that times a 7, but I don't think I'm going to right now because I want to do the last one. Here's another one. Let's see. So big F of x equals sine x to the 5th. And we've really already done one like this. We know that this is the inside and this is the outside. So when we go to do the derivative, we're going to do the derivative of the outside. So we're going to bring down the 5, leave the inside inside, subtract 1 from the exponent, and then multiply times the derivative of sine x, which is cosine x. And so that's the answer. Now, I guess it can get kind of tricky when you use the chain rule with the quotient rule or the product rule or combinations. It can get messy. I'll try not to do anything real messy on the test. You might have some messy ones in your homework. So we're using the chain rule with the quotient rule. And so I want to find the derivative. Sorry. So I'm going to find the derivative. And g of x is equal to x squared over x plus 1 to the 5th. So we're going to have to use the power rule because our outside function is an exponent. But then we're going to have to use the quotient rule because the inside is a quotient. So, you can see that the inside whatever, is the g of x, which is the x squared over x plus 1. And the outside, the little f of x, is just x to the 5th. Okay, so now we're ready to start differentiating. So g prime x, let me move this up because we're going to run out of room anyways if we're not careful. We might anyways, but g prime x over equals, so I'm going to bring down the 5, leave the inside inside, subtract 1 from the exponent, and then we've got to, and I'm going to write in the step, we've got to do the derivative, find the derivative of the x squared over x plus 1. So we're going to have to use the quotient rule to do that. So my g prime x equals 5 times x squared over x plus 1 to the 4th, and then I'm going to do the derivative of this. So I do the bottom times the derivative of the top, this is quotient rule, minus the top times the derivative of the bottom. And that's all over the bottom squared. Now, then that's all the calculus. The rest of it is just simplifying it or getting it into a factored form. And the reason we want to do that is, like, you know, if you're trying to find where it has a horizontal tangent, then you have to set it equal to 0, the derivative equal to 0 and solve. And part of the solving is going to be factoring it. So, I mean, I guess we could, you know, just set this part equal to 0 and set this part equal to 0. But let me just show you how you could factor it. And you can forget about this if you want. I won't give you this on a test, but I think some of your homework's like this. So first of all, I've got the x squared over x plus 1 to the 4th. And then I'm going to go ahead and I'm going to multiply. So I've got a 2x squared. And I've got a 2x. And I've got a minus x squared. And that's all over x plus 1 squared. Okay, so I got 5. And then I'll just rewrite this for a second. And then I'm going to combine like terms. So I'm just going to have an x squared plus 2x over x plus 1 squared. Okay, I'm going to go ahead, because this is the 4th power, I'm going to go ahead and raise this quotient to the 4th power. So I've got 5 times, you know, when you raise a power to a power, you multiply. So this is going to be x to the 8th over x plus 1 to the 4th. And then I've got that multiplied times x squared plus 2x over x plus 1 squared. And you know what? I'm going to go ahead and just factor the x out of here. So we could go ahead and just do that in this step. Okay, so I'm going to factor the x out. So I'll have x times x plus 2. Okay, so I can go ahead then, let me just put a paren here, and go 5. And if I combine the x's, that'll give me x to the 9th and I'll have an x plus 2 in the numerator, and then I'm going to combine the denominators because they're the same base. They're x plus 1's the base, so I can combine that. So this is just algebra, x plus 1, and then when you combine like bases, or when you multiply like bases, you add the exponents. And so if I were to be, if I asked you, I wouldn't probably give you one this messy on the test, but it could be in homework. And if it said, where does g of x have a horizontal tangent line? Well, since we've got it in factored form, it'll be easier for us to solve. So we take, the derivative, which is this g prime x. We take the derivative. And we set it equal to 0. Because remember, our horizontal line has a slope of 0. So then using the zero product property, now when a rational expression like this is going to be 0 is when the numerator is 0. It's undefined when the denominator is 0. Or you could just go ahead and cross multiply and get rid of this denominator, because it's when the numerator is equal to 0. Okay, and I can go ahead and divide by 5. Now I can't divide by x because x could be 0, and that is one of the solutions. But I can get rid of the constant here. So then what I have is x to the 9th times x plus 2 equals 0. And then using the zero product property, I'm going to get my two answers, x equals 0 and x equal minus 2. So that's where the tangent line has, those are the x values for where the tangent line has a horizontal tangent, or where the function has a horizontal tangent. Now, if you wanted to go back and find the y value, you would have, if it asked for the point, so it's asking for the y value, you would have to go back to the original function, g of x, and plug the x value, like you could plug 0 in here and you get 0. And you can also plug the minus 2 in here, and it would give you the y value. Okay, but I'll do that right now. So that's how you do that problem. Okay, let's go to the next example. And this one is messy. I didn't give you one like this on the test. There might be one like this in the homework. I can't remember. Maybe I took it out because it is messy. I'll show it to you though. So in this case, we're using the chain rule with the product rule. Now, it's not hard to do the calculus, or not that hard. It's getting it in factored form. So we've got a product, and the product, we've got things raised to, or factors raised to a power. So what we've got here is a product of composite functions. Now the product in this case is on the outside. It could be that you've got a product on the inside of a function. So anyways, let's try this one. So y prime, we're going to go first thing, using the product rule, times the derivative of the second thing. So I'll just write this out. And then the second thing times the derivative of the first thing. Okay. And so even within, I'm gonna have to use a chain rule here, and I'm gonna have to use chain rule here. So my y prime is going to be equal to 5x minus 4 to the fourth, and then I'm doing the derivative of this. So I've got to use a chain rule here because I've got a composite. So I'll bring down the minus 3. So let me just say right here, this is where I've got to use the chain rule. And also right here. Okay, so I've got minus 3 times 7x squared minus 2, subtract 1 from the exponent, and then multiply times the derivative of the inside. Now that's just the first part. So I've got this times the derivative of this. So bring down the minus 3, subtract 1 from the exponent, times the derivative of the inside, plus the other part, which is this part over here, but I'm going to write it below. We've got the 7x squared minus 2 raised to the minus 3. And then I'm going to do the derivative of this. So I'm going to bring down the 4, multiply it times the 5x minus 4, subtract 1 from the exponent, and then multiply times the derivative of the inside. So this is what I have. Now, the calculus is done. The rest of it is going to be algebra. So I've got the 5x minus 4 to the fourth, and I'm going to go ahead and distribute this minus 3. I can't do that yet. What did I want to do next? Oh, okay, I know what I was going to do next. Okay, this is what I did. I went ahead and I multiplied the 14 times the minus 3. And so that gave me a minus 42. And I've also got a factor of x. And then I've got this 7x squared minus 2 to the minus 4. And then I've got plus the 7x squared minus 2 to the negative third power. And here I went ahead and multiplied the 5 times the 4. So I have a 20 times 5x minus 4 to the third power. Okay, now if you notice, there's a 5x minus 4 factor here, and there's a 5x minus 4 factor here. There's a 7x squared minus 2 factor here, and there's a 7x squared minus 2 factor here. So we're going to factor this. This is 2 terms. So what I'm going to do, well, first of all, I'm going to write the minus 42. Let's just write it like this. Let's put this extra step, which doesn't really do a whole lot, but I'm going to put the minus 42x. I'm just going to rewrite it with the coefficients out front. Okay, and now I'm going to factor out. And so if you remember, you factor out, it's like the greatest common factor, but it has to be a common factor. So we see that 5x minus 4 is a common factor. But what power is common to both? So you're going to have to take the smaller power. So that's the 3. Then we go to the other common factor, which is the 7x squared minus 2. And we're going to have to take the lesser of that. So that's the minus 4. And then what that is going to leave us when we do that is, and I'm going to go ahead, already got the 42 out. Yeah, let's just do this for right now. And, I know what's wrong. I can't factor that minus 42 out right now. It's only in front of this factor, so it shouldn't be in the front. So let's take that away. And then what's going to be left is the minus 42x times, there's going to be a 5x minus 4 left in the first term. And there's going to be the 20 and a 7x squared minus 2 left to the minus, or just to the first power. That's going to be left because, see, we're taking out to the minus 4. So that leaves, we're taking that out of the 7x squared minus 2 to the minus 3rd. So there's still going to be one left in here. And so then I'm going to, I can factor 2 out if I want to. It doesn't really matter. And so that's 2 times 5x minus 4 cubed times 7x squared minus 2 to the minus 4th. And then what we've got left if we do the multiplication, let's see, I think I get a minus 105x squared plus 84x plus 70x squared minus 20. Yuck, this is quite yucky, I'll admit. You know, when we teach factoring in college algebra, it really is an important thing. And so now we're going to collect like terms. You do it all through calculus. And then we're done. So, you know, there's the 3 factors. If you had to set it equal to 0, you'd have to set this equal to 0, this equal to 0. This would never be 0 because it would be in the denominator. And then you'd have to somehow solve this. You might have to use quadratic formula on this. I probably would just go ahead and use the quadratic formula on that. But I would never, ever ask you to do this on a test. There might be one in the homework that's that bad. I'm not sure. We should do these examples because this is very common. The e to the x examples. Yes. So for example, so for the first one, y is equal to e to the 10x. Now, when it's like a function like this, it's not like the outside is on the outside. This is a composite function, so we are going to need to use chain rule. If it's a composite function, we need to use the chain rule. So let's call the, say g of x is equal to 10x and f of x is equal to e to the x. So this is the outside, and this is the inside. So when you've got, you know, an exponential expression like this, the exponent is going to be the inside, and the base is going to be, or e to the x, whatever the base is, that's going to be the outside. And, you know, you could see this if you do f of g of x, you would get, you know, f of 10x. And what does f do? It goes e to whatever you have in there. So it would look like that. Okay, so now let's do the derivative. Y prime, we're going to do the derivative of the outside, but the derivative of e to the x is just e to the x. But then we're going to multiply times the derivative of the inside. And the derivative of the tangent function is secant squared x. So that's it. That's our answer. Let's do another one. Y equals e raised to the x squared. Okay, so we've got f of x equals e to the x. That's the outside. We've got g of x equals x squared. That's the inside. So then y prime, we're going to go e, because the derivative of e to the x is just e to the x. So we write that with the inside still inside, times the derivative of the inside, or the exponent. And that's what we get. So let's do another example. Y equals e to the 2x. And you can see this is the inside, this is the outside. So y prime is going to be e to the 2x times the derivative of 2x, which is 2. And that's my answer. Okay. We're going to have a new derivative law now. What is the derivative of y equal a to the x? So this is when the base is not e, but it's some other positive number. So this is a proof of how we get this derivative. This is not the calculus, so this is just rewriting it so we can prove this. So we're going to rewrite the base, which is a, as e to the natural log of a. Well, why can we do this? Well, you know, natural log is base e. And, you know, it's the same thing as e to the log base e of a. And the e and the log of e cancel each other because, you know, log of e means what power do I raise e to get a? Well, I'm raising e to that power. So this is just going to give me a. Or you can think about it, e to the x and log base e of x, they are inverse functions of each other. So they cancel each other out. So now let's start with y equal a to the x. And we're going to rewrite it. So a is e to the natural log of a. And then we're raising that to the x. So y equals e to the natural log of a times x. Because remember, when we raise a power to a power, we multiply the exponents. So now we're ready to do the derivative. Y prime, and we're going to use the chain rule. So I guess we are using calculus here, not just algebra. We go e to the natural log of a times x, then times the derivative of the inside function, which is the exponent. And that derivative is natural log of a. Now, natural log of a is just a number, depending on what a is, the base is, but that's a constant. It doesn't have x in it. So then we can rewrite this back into this form. And then what was e to the natural log of a? That's a. So y prime equals a to the x times natural log of a. And that's the part you're going to need to know is this derivative rule. So this is a new derivative rule for you to put on your study sheet. The derivative of a to the x equals a to the x times natural log of a. And it works for e to the x, because if you do the derivative of e to the x and you use this rule, it's e to the x times the natural log of e. Well, what is the natural log of e? It's 1, because it's the power that you raise e to get e. You can do that on your calculator. Natural log of e is 1. So that means it's e to the x. And we already knew that from earlier in one of the other sections. So let's do a couple of examples. With that, using that rule, okay, so we want to find y prime. And the first one, y is equal to 8 to raised to the 2 minus x squared. So we use the chain rule, and we go y prime equals, well, the derivative of, the derivative of a to the x equals a to the x times the natural log of a. So if the base isn't e, you still have to multiply times the natural log of a. I mean, you can do it with e, but the natural log of e is just 1. So I've still got 8 raised to the 2 minus x squared, but then I have to multiply times the natural log of 8. And then I have to use the chain rule, and I have to multiply times the derivative of the inside, which is going to be a minus 2x. The derivative of 2 is 0. This will be a minus 2x. And then I can just rewrite it. I can write, usually you'd write the log, really, usually you'd write like this, the minus 2 log of 8, or natural log of 8 is just a constant. And then you'd write the x, and then you'd write the 8. Then you can write the 8 raised to the 2 minus x squared. Okay. That's it. Okay, let's look at another one. And so y equal 2 raised to the x squared. So here we've got the base of 2. We're going to use this derivative log in, and we're going to use the chain rule. So, we're using the chain rule on all these. And, you should always ask yourself, do you use the chain rule? In this case, yes, we do. But as you keep going, you should always ask yourself, get used to asking yourself, do I have a composite function? Do I need to use the chain rule? And, do I have a product? Do I need to use the product rule? Kind of analyze the problem and figure out what rules you're going to need to use. So, yes, chain rule. Yes. So we're going to go y prime equals 2 to the x squared times natural log of 2. So that's the derivative of the outside function, because it's the, forget that that's x squared up there, but it's the base raised to the whatever times the natural log of 2. But then we've got to, go ahead and use chain rule and do the derivative of the exponent, which is the inside function. And so y prime equals 2 natural log of 2 times x times 2 raised to the x squared. And that's my answer. Okay, sometimes we do use chain rule twice. Here's some examples of that. Okay, so this is why it's called the chain rule. To find, this is a derivative of 3 functions, f, g, and h. I mean, it's a composite of 3 functions. So in this case, it's a composite of 3 functions. So the way it goes is you do the derivative of the outside with its inside times the derivative of the middle one with its insides inside, finally times the derivative of the inside. So it's like you have 3 functions here. You have an outside, a middle, and an inside. So let's do some examples of this. So the first one says y equals e to the tangent of square root of x. So it's important to recognize that there's 3 functions here, functions of x. And why are there 3? Well, there's the outside, which is f of x equals e to the x, that's the outside. There's the middle, which let's call it g of x, equals tan x. And then there's the inside, which is, let's call it h of x, equals the square root of x, or we're going to have to rewrite it as x to the 1/2. Okay, so we're going to use this rule right here. So y prime is going to be the derivative of the outside. So the derivative of e to the x is just e to the x. So, and I'm keeping the inside inside. Then I go to the middle, which is the tangent function, and the derivative of it is secant squared, and I keep the inside inside. Then I go to the inside. I bring down the 1/2 because it's x to the 1/2, and then I subtract 1 from the exponent. Okay, so that's it. It goes in a chain. So we do the derivative of the outside, which is e to the x, so it's e to the whatever was here. Its insides times the derivative tangent, that's the middle function, so that's secant squared, square root of x, times the derivative of the inside, 1/2 x to the minus 1/2. And here's one. Y equals sine of sine x. Okay, so that's not a product. That is a composite of 3 functions. So the outside, the sine x, the middle, the sine x, and the inside of sine x. That's just what it happens to be. So y prime, we're going to do the derivative of the sine. So that's cosine. And we leave the inside inside. Then we do the derivative of the middle, which is sine. And we leave its insides inside, times the derivative of the inside. And the derivative of sine x is cosine x. And that's the end. Okay. Another example. Okay, so here's an example that we do a lot. Find the x-coordinate of all points on the curve at which the tangent line is horizontal. So we need to remember when we see this, tangent line is horizontal, we're going to have to find the derivative and set it equal to 0 and solve. And then also pay attention, does it ask for the x-coordinate? Does it ask for the y-coordinate? Does it ask for both? If it asks for the point, that means the x and the y coordinate, but this is only asking for the x coordinate. So what we want to do is we want to find y prime, set y prime equal to 0, and then solve for x. We're going to use this formula in a minute. So here's what y is. Y is equal to sine of 2x minus 2 sine x. Excuse me. We're going to have to use a chain rule right here. That's really the only place, because this is a composite, because it has a 2x instead of an x. If it's just x, then it's not a composite. If the inside is just x. So we do the derivative of the outside. So derivative of sine is cosine with the inside times the derivative of the inside minus 2, and the derivative of sine x again is cosine x. And then we're going to set that equal to 0. So, when you've got just a constant times x, you end up just multiplying times that constant. So I'm going to factor out a 2. And then I've got cosine of 2x minus cosine of x equals 0. Can divide both sides by 2 and just get rid of that 2. So I've got cosine of 2x minus cosine of x equals 0. Now, this is where I'm going to use the identity. And if you go back to trig, these are the double angle formulas. For cosine of 2x, this is 2 theta, but same with an x. There's 3 forms. What form with it we want to use is this one. Why? Because this is a cosine x, and if I use this formula, I'll only have cosine x, and I won't have a sine x. So I'm going to rewrite this as 2 cosine squared x minus 1. And then I've got the minus cosine x, and it's equal to 0. This is a quadratic. It's a quadratic equation, or it's in the form of a quadratic. The only thing that's different is instead of like x squared, we've got cosine x squared. So I'm going to rewrite it in this order. And you see it is a quadratic. And, you can do a substitution if you want. You can let u equal cosine x. Then it would be in this form. 2u squared minus u minus 1 equals 0. And that's a u. And you could factor that. I'm going to go ahead and just factor this without doing it with the substitution. So it's 2 cosine x plus 1 times cosine x minus 1 equals 0. And so using the 0 product property, we're going to get cosine x equal minus 1/2 and cosine x equal 1. So you want to think unit circle. Think about where the cosine is negative 1/2, and that's going to be at 2 pi over 3. But since we can keep going around the unit circle, we need to add and subtract 2 in pi, because that would get us back to the same point. And then the other place that the cosine x is a negative 1/2 is at 4 pi over 3. My voice is going. Then you go plus or minus 2 in pi. Now, that takes care of this one. Now, cosine x equal 1, that happens at x equals 0. And you'd have to go plus or minus 2 in pi. So these are the solutions. This one, this one, this one. 3 solutions. Well, 3 forms of the solutions. There's really infinitely many solutions because you can add this 2 in pi. And n is just an integer. We use n for an integer a lot. Okay, last example. This is a vigorous chapter and it's important too. Or vigorous section, I should say. Okay, if f and g are the functions whose graphs are shown, so there's f and g, let u equal this composite of f with g, v equal this composite of g with f, and this w equal the composite of g with itself. We want to find each derivative if it exists. If it does not exist, explain why. So I'm going to do the first one, and that's u prime of 1. Well, u of x is equal to f of g of x. And so u prime x, using the chain rule, equals f prime with g of x inside times the derivative of the inside. Well, we're trying to find that at 1. So u prime at 1, we'll just substitute in a 1 here, f prime of g of 1 times g prime of 1. Okay, so we've got to figure out what g of 1 is. So let's look at g. And here's where g is equal to 1. So g of 1 is right here. So g of 1 means the y value. So that's 1, 2, 3. So this is going to be f prime of 3 times g prime of 1. Now, when it says f prime at a number, we've got to figure out what the derivative is at that x value. Luckily, these are all like pieced together, but they're linear. It's like a piecewise function where they're all linear. So if you look at f prime at 3, you need to go over to where the x is 3 and go up to f. And then we need to find the slope of this line. So if we were to look like going from here to here, because these are places that are on the grid, you can see that it's going downwards and it goes down 1 and it goes over 1, 1, 2, 3, 4. So this is going to equal minus 1/4. Then g prime of 1, so we go to where x is 1, and we want to find the slope of this. And so, like you can think of it from here to here. This slope is going to be, we go down 3 and we go over 1. So it's going to be a minus 3. And so that's going to give me a positive 3/4. And that's the way we're going to do these. We can do b, which is b prime of 1. So it's going to equal O, and V is G of f of x. And so V prime of 1 is going to be G prime of f of x times f prime x and so V prime, or that's just V prime of x. And then let's do V prime of 1. V prime of 1, was it 1? Yeah, V prime of 1 is going to be equal to G prime of f of 1 times f prime of 1. Okay, now what is f of 1? So we've got to look on f, which now I've got stuff written everywhere, so it's kind of hard to tell. But f of 1 is, or f of 1 is right here, and that value is 2. So this is going to be G prime of 2 times f prime at 1. So we've got to find these slopes again. And so G prime at 2, that's really going to be the same thing as what we got before, isn't it? So wait a minute. No, sorry. G prime at 2. Oh, no. G prime at 2. Here's 2. What is G prime at 2? There's a sharp, isn't there a sharp corner? But G prime at 2 does not exist. So that means that this whole thing doesn't exist. G prime of 1 does not exist. Okay, and then we'll do one more, that other one that they say. So let me just write it down here. This is C. And we've got W of x, which is G of x. So it's a composite of a function with itself, which we can have. And so W prime, and they want W prime at 1, is going to be equal to G prime of G of 1 times G prime of 1. I think we got G prime of 1 up here. Isn't G prime or G of 1? Let's just go look. Here's G of 1, and G of 1 is equal to 3. So what we want to do is get G prime at 3 times G prime at 1. Okay, so G prime of 3, we haven't found that before, but G prime at 3 is going to be the slope of this. So if we look like from there to there, you could see that the slope you go up to, this is a positive slope, and you go over 1, 2, 3. So that's 2/3. So then G prime of 3 is going to be equal to 2/3. And then G prime at 1, we had already figured that out. That was -3. And then that's going to give me a -2. So I've got all my answers there. Lopsided, but that's how you do a problem. We did one before with the product and one with the quotient. So this is how you do it with the chain rule. Okay, now that's it for this section. I know it's a lot of work. It's really important section. So that's it for tonight, guys. See you later.